This is problem 2. Problem 2 would look daunting at first, but you'll suddenly realize that all you pretty much have to do is just reprove RSA, but with n equals p, which is actually simpler in a way. And notice that p is a 1024-bit number, so usually when you deal with runtimes, you not only have to consider the number itself, but how many bits it has. And it'll come handy in the later sections, so remember that number. And let's get started. So recall from the original RSA that you have a message x that is within the range of the number n that you choose. And n is a large prime, right, of p and q. But here you're given that n is p, so you can forget about q. All right. You also had an encryption function, right? And this is e of any message equals x to the e mod n, which is x to the e mod p in this problem. And we can call this result y. And so the decryption becomes d of y equals to y of d mod p, where d equals to e inverse mod p minus 1. So basically we just modified everything by getting rid of q, which is okay. And then I tried to add this y equals this result just to explain the notation a bit more clearly in case you didn't get it from the lecture notes. And so all we have to do is prove that when we do x of ed, we get x mod p. So how do we go about doing that? Recall from the RSA proof that you had x to the ed equals to x to the k times p minus 1 plus 1. Where did that come from? Well, you know that e times d is equal to 1 mod p minus 1 because e inverse equals d. So this is basically just saying that we expand 1 to 1 plus k p minus 1 regularly. So we're dealing with things regularly here. And then this is just equivalent to x times x to the k p minus 1. Now, if we notice that this is a p minus 1, we can utilize mod p as p is prime to use Fermat's little theorem. So after applying Fermat's little theorem, sorry for the notation, we get x by itself, x times 1, which is equal to x mod p. Now, if x is a multiple of p, then x just goes to 0, right? So you have x times 0. This x also goes to 0. And this is just basically 0. This is just a separate case you need to do because you need this a to be relatively prime to p. So that's why you have a separate case for this. And otherwise, we can just say if x is not a multiple of p. And great, that completes the proof. If you want a more formal and organized version, you can view the written solutions online. But I just wanted to make sure the notation was clear and that you could follow every step of the proof clearly. So we justified this step because you're expanding a mod. And the next step is basically just taking this exponent out here. The step after that is Fermat's little theorem, and then we split it into cases. Cool. Part 2 of problem 2, we're trying to compute d, and recall that d is e inverse mod p minus 1. So which algorithm is best at systematically calculating inverses? Well, it's the extended GCD or EGCD. And the reason why is you pass in n and then bx equals d into this formula. And while it calculates the GCD, which is d, it also calculates these two numbers for you. And so if you have two numbers that are relatively prime to each other, then d is 1, and then after that you mod both sides by n. So this becomes 0 plus b x mod n equals to 1 mod n. And that's how you find the inverse. So the b that results from the algorithm will be your inverse. So we use the EGCD, and how many iterations would it take? Well, we see that you have a recursive call here, which uses mod, and if you read the lecture notes, I made an excerpt here, where they showed that the normal GCD algorithm runs 2n times, right? Because after two recursive calls, the larger argument is smaller by at least a factor of 2. Now notice here that you need two recursive calls. Why? Because there's a swap that goes on if you don't, if one number is really close to another. So then that's why you need to make sure you have two recursive calls. Therefore, we have 2n times, where n is the number of bits. Because if you lower by a factor of 2, that's basically removing 1 bit. So factor of 2 is very similar to 1 bit. And finally, since we're given the fact that p is a 1024-bit number, this will add up to, this will multiply out to 2048 iterations. And that is part 2. Now part 3 is really simple. You're trying to recover x, and remember how our scheme worked. We have the encryption, the encrypted message that goes through the algorithm, the encryption algorithm, and gets a power e, right, mod p. So when we try to decrypt it, we exponentiate it by d mod p. And where did d come from? Remember that d came from e inverse mod p minus 1. So we can know for sure that d must be less than p minus 1. And so approximately how many iterations, we can cap this with an upper bound. So when we do exponential squaring, right, remember that we have a2, and then we can calculate a4, and then a8 after that with 3 calculations. If you go on, then you'll realize that you lose a bit every time because you decrease by you increase the exponent calculated by a factor of 2. So factor of 2 again in exponent increase is very similar to 1 bit. And since d is less than p minus 1, d is less than or perhaps equal to 1024 bits. D's number of bits, sorry. And so therefore, since you lose a bit for every iteration of exponential squaring, you'd need 1024 iterations. And that is the answer. Now for part 4, can Eve recover the original message in a reasonable amount of time? Well, from part 2 we have 2048 iterations, and from part 3 we have 1024. Added together, this is about 3072 iterations, and each iteration is just some arithmetic, right? So the numbers we're working with are less than 1024 bits, which is a reasonable number. So basically the point is, like, we didn't need to try out 2 to the 1024 combinations. We only needed this many iterations. And so therefore, this scheme does not work.